Yes,
Okay, so let us begin with the chemistry class. Uh, I started the chapter 5, states of matter, gases, and liquids yesterday in the previous class, and today is the second day. It's a morning class. I have one more class with you all in the afternoon also. And in my previous class, I had told you regarding the Dalton's law of partial traces. Today, I'm going to discuss with you Graham's law of diffusion and diffusion. But before going into the statement of Graham's law, let us first understand what is diffusion, what is effusion. On your screen, you can see there is a diagrammatic illustration to explain diffusion and effusion. Now, what is diffusion? Diffusion, as it is the mixing of gas molecules by a random motion under conditions where molecular collisions occur. Random. Okay. Whereas effusion, it is the escape of a gas. The gas is here through a pinhole into a vacuum without molecular collisions. So these are two important words under Graham's law of diffusion and effusion of gases. Now, now coming to the statement of Graham's law. Now, according to Graham's law, but before that, let us try to understand over here. Diffusion is a spontaneous mixing. Diffusion is a spontaneous mixing. Remember that. Diffusion is spontaneous mixing. Diffusion is spontaneous. Whereas effusion is whereas effusion is it is a gradual movement, of gas molecules. Okay, so this must be very clear in your mind. Now, coming to the law, the Graham's law. The Graham's law has been stated as at constant temperature and pressure. At constant temperature and pressure, at constant temperature and pressure, the of diffusion, the rate of diffusion and effusion, of a gas is inversely proportional, is inversely proportional, inversely proportional to the square, root of its density. So this law you put it in your mind today only. At constant temperature, if the temperature is constant, the rate of diffusion, let it be small r, it is inversely proportional to the square root of the density of the gas. So this is the relationship according to Graham's law for the diffusion and effusion of gases. Now, this R stands for the rate of diffusion and this D stands for the density of the gas. Now, if we move ahead and work with this relationship with regard to Graham's law of diffusion and effusion, so we can take two different gases over here for two different gases, say gas 1 and gas 2. Okay, so here I can write two equations. R1, rate of diffusion of the first gas, is inversely proportional to square root of its density d1, and R2 will be inversely proportional to the square root of density of gas 2. Now, if you combine these two equations, if you combine this one and this one into a ratio, I can get R1 by R2 is equal to, okay, it comes to root under d2 by d1. Okay. Now this is density. This is density. Whenever we talk about density of the gas, we're talking about its vapor density. So if I multiply this density by 2d2, twice into vapor density is molecular mass. So here also twice d1, twice d2. Okay. So this twice into vapor density become molecular weight. So I can transform this equation into the other form, m2, molecular mass of gas 2 divided by molecular mass of gas 1. Okay, so that is how we get, after comparison, R1 by R2 is equal to root under m2 by m1. Okay, so that is how we can compare. We can compare the rate of diffusion and effusion of two gases with respect to their molecular masses. Now, if we proceed further, comparison of time for diffusion taken for the same volume of two gases. If the volume of the gases diffusing are same, that time we can compare the time also. So this is one case over here. So I'm going to write it down. Comparison of time of diffusion. Comparison of time of diffusion taken for the same volume of two gases. So for this, if we take the two gases, then we can compare the time as well. So here we can have R1 by R2 is equal to density. We convert this density. Okay, so we are putting in time over there. So I can have V1, that is volume is same. Okay, same volume. So it will be V only. V by T1 divided by V by T2. That is equal to root under d2 by d1. That is equal to root under m2 by m1. Okay, now if you proceed further to simplify this relationship, the volume will cancel. And then we can get the equation in terms of time. T2 by T1 will be equal to root under d2 by d1, that is equal to root under m2 by m1. So this is under first case where we are comparing time of diffusion taken for the same volume of two gases. Okay. Now the second case is comparison. Comparison of volumes. Comparison of volumes of the gases. That diffuse in same time. So whenever there is same volume, you remember this formula. Okay. Now another formula is the comparison of volumes of the gases that diffuse in the same time. So over here, I'll just write down the final formula only. No need for the derivation. R1 by R2 is equal to V1 by V2, that is equal to root under D2 by D1, that is equal to root under M2 by M1. So whenever you compare the volumes under the same time for the gases diffusing, so you have to remember this formula for the numericals part. Okay. Now the third case is over here, when pressure is not constant. When pressure is not constant. When pressure is not constant, then we know the rate of diffusion is inversely proportional to its molecular mass. And we also know the rate of diffusion is directly proportional to its pressure. So if you combine these two relationship, okay, if you on combining these two equations for two different gases, the final formula becomes R1 by R2 is equal to P1 by P2 under root, okay, M2 by M1. So when the pressure is constant, remember this is the formula that we'll have to use, okay. Not constant, sorry. The pressure is not constant, pressure is changing, then you have to use this formula. So this was a qualitative and what do you call discussion about the Graham's law of diffusion and diffusion of gases. Now moving further to the next topic in this chapter with regard to kinetic molecular theory of gases. Now you can have a look at the postulates from a textbook also with regard to kinetic molecular theory of gases. It is not that difficult. Okay, there are around 6-7 postulates which have been mentioned in your textbooks. Now, if you look at the textbooks, most probably on page number, I'll tell you the page number. The textbook, my textbook, it is given on page number over here, 321. Kinetic molecular theory of gases, the microscopic model of an atom. So there are around, see, plenty of them are there. There are around 10 postulates. A gas, it is generally composed of a large number of extremely small particles called molecules. The molecules of a gas remain quite far apart from one another. This gives rise to an intermolecular space in the gas. The molecules of a gas are so small and the intermolecular space is comparatively so large that the actual volume of the molecules is negligible, very small, minute, as compared to the total volume of the gas. The fourth one, the molecules of a gas do not attract one another and move independently of each other. Fifth one, the molecules are always in a state of continuous random rapid motion except in the gas at absolute temperature in all directions. The molecules move randomly in straight lines. During the motion, they collide with one another and with the walls of the container. These collisions, they change the direction of movement of the molecules. Then, number 7, the molecular collisions they are perfectly elastic. They bounce. During the collision of two molecules, no loss of kinetic energy occurs. However, there may be a transfer of energy between the colliding molecules. Important point to note. The pressure exerted by a gas is due to the bombardment of the molecules on the walls of the containing vessel. The molecules of a gas possess different speeds and therefore different kinetic energies at a particular time. The average kinetic energy of a molecule in a gas is directly proportional to what? The absolute temperature of the gas. So these are some postulates which was given by Boltzmann and Maxwell, and it was called kinetic molecular theory of gases, okay, or the microscopic model. Now, after this, there is one very important equation after the kinetic molecular theory of gases, which is called the kinetic gas equation and its relationship with the average kinetic energy. Now, this I want to explain it from the book itself, the kinetic gas equation. So, on the basis of the postulates of kinetic molecular theory and on the basis of a detailed mathematical treatment of the theory, which is not required in our syllabus, the derivation is of not importance in chemistry. A very important equation has been derived, and this equation, if you see on the screen, PV is equal to 1/3 mnu square, where P stands for the pressure of the gas, V stands for the volume of the gas, and this M stands for the mass of a single molecule of a gas. And this small n stands for number of molecules present in the volume capital V, and this U stands for root mean square velocity of the molecules. Now, what is the meaning of root mean square velocity? Now, this root mean square velocity, it means The square root of the mean of the squares. Let me explain this on the slide over here. The root mean square on the next page. Just a minute. Let me explain this root mean square. Now this root mean square, the root mean square, we write it as U, okay, U RMS. Now this root mean square means the square root of the mean of the squares of the speeds of different gas molecules at a given temperature. So the formula is like this: URMS is equal to under root N1 V1 square plus N2 V2 square plus N3 V3 square, and it goes on, of all the gas molecules divided by N1 plus N2 plus N3 plus it goes on. Now there is a summarized formula for the root mean square. It is given a short formula: root mean square is equal to root under thrice RT by capital M, or if you write in terms of pressure and volume, root under thrice PV by M. So this is one formula which you'll have to remember. This R is a constant. It is a gas constant. Okay. This M is the molecular mass. P is the pressure. V is the volume. Okay. So I think the idea of root mean square is clear to all of you. Now moving to the textbook over there. Moving to the textbook. Here PV is equal to 1/3 mnu square. M stands for the mass of single molecule. This is very small m. Okay. Mass of a single molecule of the gas, and small n stands for number of molecules present in volume V, and this U stands for root mean square velocity of the molecules. Okay. Now this equation has been derived purely on the basis of the postulates of this kinetic molecular theory. No gas law has been used for the derivation of this equation. Remember that. Therefore, this equation can be used for the derivation and explanation of various gas laws which lacked a theoretical support behind them. Now, if you take 1 mole of a gas containing n, Avogadro's number of molecules, therefore 1 mole of a gas, kinetic gas equation can be written in this form also. So 1 by 3 m capital N, that is Avogadro's number, into U square. Now the total kinetic energy over here, the total kinetic energy of 1 mole of a gas, the average kinetic energy of a single is given by this formula: Ek is equal to half mu square. So if you work out and find the total kinetic energy, then we can come to an equation like this. So for 1 mole of a gas, since PV is equal to RT, putting the value of PV in the above equation, we can get, instead of PV, put RT. RT is 2 by 3 Ek, or Ek means the total kinetic energy of 1 molecule of a gas, that is equal to 3 by 2 RT. Okay, this is one equation. After that, we have got average kinetic energy of a single molecule of a gas. Now, again, the average kinetic energy of a single molecule, that is Ek, can be obtained by putting the value of Ek dash from equation 5.28 earlier. Equation 5.28 is here. Then, if you put all the values and substitute, you will get a final form which you'll have to remember: E dash K is equal to 3 by 2 KT, where K, this K which you see, this K over here, it is called Boltzmann's constant. It is called Boltzmann constant. Its value in the SI system is 1.3807 into 10 power minus 23 joules per Kelvin. Now both equations 5.31 and 32 imply that the total kinetic energy of 1 mole of a gas, as well as the average kinetic energy of one molecule, is directly proportional to its absolute temperature. So we know at absolute zero, temperature is 0, so we have Ek is 0, Ek is also 0. Okay, so this is what you have to remember. Now there are some simple numericals. We calculate the average kinetic energy, so please go through this on your own. It is not difficult. Direct application of formula. Example 5.31 also you can go through carefully. And then there is on page number 323 deduction. Deduction and explanation of gas laws on the basis of kinetic molecular theory. This deduction is given, which is not required. Derivation is not required. Okay, explanation is given. You may read through this explanation: Charles' law, Okay, this is Boyle's law. Okay, now we come to the next topic. Okay, over here, next topic, which is called Maxwell's distribution of velocities, which I'll explain you from the slide. Okay, now have a look. This is with regard to root mean square velocity. Remember this formula. Okay, okay, this formula is also important. Then we come to Maxwell's distribution of velocities. Now, under this Maxwell distribution of velocities of molecular speeds of gases, the speed of different gas molecules is different at given temperature. Their speed also changes during collision. Okay, so if you look at this plot, fraction of molecules versus velocity. If the fraction of molecules, okay, it is, this is the curve over here. Most probable velocity is here. All these peaks, average velocity, root mean square velocity. Okay, so temperature 1, temperature 2, temperature 3. So you can see over there, temperature 2 is higher than temperature 1. Temperature 3 is still higher than temperature 2 and 1. So with the increase of temperature, what is happening? What is happening? The velocities are changing. The velocities are becoming higher. Okay, the velocities are becoming, that is the main concept to be understood over here. Now, here the point-wise explanation. The molecules present in a given sample of a gas move with different velocities in all possible directions. Velocities and directions of molecules keep on changing due to intermolecular collisions. Hence, it is impossible to find out the individual velocity of each molecule. It is, however, possible to predict the fraction of the total number of molecules having specific velocities at a particular temperature. As shown by this curve over here, the gases show ideal behavior at low temperatures or large volumes. So if the volume is large, and temperature is low, the gases will show ideal behavior. So this could be a question in a multiple choice. Since the volume of molecules can be regulated and at high temperatures, since intermolecular forces decreases. So this is another important point where at high temperatures we can neglect the what you call volume of the gas molecules. Okay, and since intermolecular forces are decreases at high volume. Okay, so this was with respect to Maxwell distribution of molecular speeds. Now from this I would like to draw important conclusions. So Maxwell's Maxwell's distribution curve conclusions. If you plot a graph of fraction of molecules versus the velocity or the speed, then there are some conclusions drawn. The first conclusion is like this: the speed the speed possessed the speed possessed by the maximum fraction by the maximum fraction of the gas molecules is called most probable speed is called most probable speed. The speed possessed by the maximum fraction of the gas molecules. Okay, the maximum fraction is having what speed? That is called the most probable speed. The second conclusion is like this: the fraction of the gas molecules, the fraction of the gas molecules having very small or high speed is small is small. So this is the second conclusion from the Maxwell's distribution curve for the molecular speeds of gases. the fraction of the gas molecules having very small or high speed is small, only very less of them. Okay. Then the third conclusion is like this: on increasing the temperature, on increasing the temperature, the curve shifts, the curve shifts, the curve shifts towards right, towards right. So this we have already seen from the curve over there. So after the conclusions, I think the idea is clear. At lower temperatures, the volume is more. Volume more means the fraction of molecules occupying the space, it is more. With the increase in temperature, the curve is shifting. The curve is shifting towards the right. That means with rise of temperature, the fraction of molecules colliding, it is becoming lesser and lesser. It is becoming lesser and lesser at higher temperatures. Okay, because of more energy possessed by the gas. Now this was with respect to Maxwell distribution of molecular speeds. Now behavior of real gases. We'll come to the next topic now, which is called behavior of what do you call real gases, deviation from ideal gas behavior. Now let me write it down. Behavior of real gases, deviation from ideal gas behavior, ideal gas behavior. So this is one important topic. Now we know gases obey the gas laws or the gas equation under all conditions of temperature and pressure. So if these gases they obey the gas equation, the gas equation is PV is equal to nRT. Okay, if they obey this gas equation, then these gases are called what? Real gases. Now they tend towards ideality at low pressure and high temperature. Now example, carbon dioxide. If we talk about carbon dioxide gas or sulfur dioxide gas or ammonia gas, these are soluble in water and they can be easily liquefied. Now such gases which are soluble in water and can be easily liquefied, they show large deviation. They show large deviation from the real gas behavior other than the gases like hydrogen or nitrogen or oxygen, which are these gases are what? Insoluble in water and are not easily liquefied. So this is one important point to remember. So I repeat this once again. We know gases they obey the gas laws or gas equation, which is PV is equal to nRT under all conditions of temperature and pressure. Okay. Now these gases, if they obey the ideal gas equation PV is equal to nRT, then they are called what? Real gases. Now they tend towards ideality at low temperature, low pressure and high temperature. So if the pressure is low pressure and high temperature. So over here they tend to become ideal gas under low pressure and high temperature. Okay, now there are some exceptions. Carbon dioxide, sulfur dioxide, ammonia, these are gases which are soluble in water and can be easily liquefied. And such gases they show larger deviation. The deviation of these gases is more than the deviation of these gases which are insoluble in water and what they cannot be easily liquefied. Okay, this you must remember. Now the study of deviation from ideal behavior, it is an important thing in this chapter. So there is a convenient way of showing the deviation of gas from ideal behavior. Now this I will refer to the textbook for a while and then I'll proceed further with the explanation. So have a look at the book. This Maxwell distribution of velocities I've already explained to you. Okay. See, with the increase of temperature, what is happening? The volume occupied is becoming less and the velocity is moving, it is becoming higher. So the number of gas molecules undergoing collision is becoming lesser and lesser. Different types of velocities you can read from the textbook only. That will help you understand the concept. Root mean square velocity is here. Okay, this is not required. Then coming to this one, I was talking about non-ideal behavior of gases and Van der Waals equation. Ideal and real gases. The gas which obeys the gas laws and the gas equation under all set of conditions of temperature and pressure is said to be an ideal gas or a perfect gas. The concept of ideal gas is only an imagination. Among all the known gases, no gas is ideal. Remember that. Almost all gases show significant deviation from ideal behavior. The known gases do obey gas laws and the gas equation, but under definite set of conditions. No gas is yet known which obeys these gas laws under all conditions of temperature and pressure. Therefore, the so-called ideal gas or perfect gas is only an imaginary gas. A very, very important point. The so-called ideal gas or a perfect gas is an imagination only. You can just imagine. Okay, it is an imaginary gas. All the known gases like hydrogen, nitrogen, which are, they fail to obey the gas law because they're insoluble in water. They're insoluble in water. One important point is that. Okay, and they are difficult to liquefy. And the ideal gas equation, under all set of conditions, they are termed as non-ideal or real gases. Okay. Now, deviation of real gases from ideal behavior. For this deviation, there is a factor which is called compressibility factor, Z. The deviation of real gases from the ideal gas behavior can conveniently be expressed in terms of a factor which is known as compressibility factor. Z is equal to PV by nRT. The value of compressibility factor depends upon the nature of the gas, what type of gas you're using. So remember, for an ideal gas, the compressibility factor it is 1 for the multiple choice question. Okay. For a real gas, the compressibility factor is not equal to 1. It is either of these, either Z is equal to 1, greater than 1, or Z is less than 1. For a real gas, remember, the Z often exhibits both positive and negative deviation. In case of positive deviation, the compressibility factor is greater than 1, while in the case of negative deviation, the compressibility factor is less than 1. So, the deviation of real gases from ideal behavior depends upon two factors, remember, pressure and temperature. So, this can be studied in this next subsection, effect of pressure on the deviation of the gas. So, if you look at this paragraph over here, the value of Z, look at this. Okay, this is a plot of Z versus P. So when the pressure is increased, there is a curve coming over here. Okay, for gases like hydrogen, it is a straight line. Z compressibility factor versus pressure, it is a straight line. For nitrogen, there is a curve. Okay, helium, it is a straight line. Carbon dioxide, there is a curve. Okay, ideal gas when Z is equal to 1. Okay, so this is a negative deviation. This negative deviation, nitrogen also has negative deviation, but the rest, helium, hydrogen, and neon, they are positive deviation. So that is what is explained according to this what do you call deviation of compression factor with respect to pressure. Okay, so here, okay, never mind. We come to the what do you call this? I'll explain it from here. Now, what is the cause of deviation from ideal behavior? Now, the main cause over here of deviation of gases from ideal behavior is the force of attraction. The force of attraction or repulsion between the molecules may not be negligible. So, this I'm going to write it down. Cause of deviation. Cause of deviation of gases from ideal behavior. So the first cause is like this. The force of attraction. The force of attraction. The force of attraction or repulsion. Or repulsion between the molecules. Between the molecules. Between the molecules may not be negligible. May not be negligible. That is, it may have a considerable value. The second cause, the volume occupied by the gas may be so small, when I talk about force, I am talking about pressure, remember that. And here I am talking about volume. The volume occupied by the gas may be so small that the volume occupied by the molecules may not be negligible. Okay, so that is why there is a correction. In the equation of state for real gases, and that's how we get Van der Waals equation. Okay, so because of these two causes, the force of attraction not negligible, the volume occupied by the gas molecules may not be negligible. So this also has to be taken into account. That is why the equation, ideal gas equation, it is corrected, and we have correction for volume and correction for pressure. Okay, now this correction for volume and correction for pressure, I will explain you all in the afternoon class at 12 o'clock. Okay, and then we'll proceed further in this chapter. Okay, now that will need more time, because if I start that equation for state for real gases, Van der Waals equation, correction and all, and I'll not be able to complete in the remaining time with whatever is left over there. Okay, so with this, I would like to end this morning class for the moment. Okay, for the moment, and in the afternoon when we meet, I will discuss with you all the Van der Waals equation. What equation? The Van der Waals equation. Am I clear? Okay. So just hang on, because I will record the attendance, and then only you may leave the class after that. Okay. Your attendance is done. You may
Thank you, sir.
join the next class. Thank you so much. Have a nice day.